High entropy oxides are a new type of ceramic materials. They are designed based on engineering configurational entropy, 5 or 5 more oxide components with near equimolar concentrations are mixed to form a single phase oxide. Because of high configurational entropy, high entropy oxide HCOs have good tolerance for effects. Like this schematic shows, in this plan view, each cation has different radius. Also, they may have different valence state, but they still stay in the same rock salt phase. So high configurational entropy offers HCOs good tolerance for cation multivalency and ionic vacancies. Besides rock salt structure, scientists have already fabricated fluoride HCOs, spinel HCOs, and even perovskite HCOs. So the HCOs have good structure and composition flexibility. All of this make HCOs good application potential in electrochemistry. For example, HCOs have been used in lithium or sodium ion batteries. HCOs can serve as anode or cathode because they have good electrochemical stability, phase stability. Also, they can accommodate more lithium or sodium ions. Besides batteries, HCOs also be used in catalyst field. For example, they can be used for catalyst dispersion. Catalyst platinum atoms can be distributed uniformly in the HCO matrix because the composition stability, and they have the cations can have more. The cations have this uniform distribution in the cation sites. Because HCOs has high temperature stability, this catalyst shows high efficiency in carbon dioxide conversion. Besides, HCO itself can serve as electrochemical electrocatalyst as well in the fuel cells with high efficiency. So so the HCOs are very promising materials used in electrochemistry, in the batteries or the catalysts. They have good phase stability, electrochemical stability, conditional design flexibility, homogeneous distribution of cations, as well as high temperature stability. Besides the structure, porous films are also important morphology in electrochemical reaction. For example, in the fuel cells, the electro reaction needs triple phase boundaries. You can see the electrons, they should provide a pathway for electrons and ions and the mass, like the oxygen, to come at the same place to make this electrode reaction happen. So they need a larger surface area. Also, for the electrode in the batteries, they want to accommodate more lithium or sodium ions to improve the capacity. For the catalyst field, the catalyst want to have more side, or they want to prevent coarsening during the reaction. So all of this need porous structures. They can have larger surface area, provide more reactive size, and leave more space for mass transport. So HCO porous films are very promising. They have very promising applications, since HCO itself has very good phase stability and the porous structure are also important using are very important in the electrochemistry reaction. So this work we want to fabricate HCO porous films using the pulsator deposition. PLD is a very is one of the physical vapor deposition. The principle is the laser will hit the surface of the target. Then there will be plasma. The plasma will jump to the surface of the substrate to deposit the target materials on the surface of substrate to make the thin films. There are some advantages of PLD technique. First, they can the fabricated films have high stoichiometry with the target materials. Besides, they can achieve various kinds of film fabrication, like epitaxial films, multi-layer films, polycrystalline, or even amorphous films, by controlling its parameters, like the temperature, pressure, energy fluence, and so on. For using PLD to make HCO films, PLD has a special advantage because they have very high T delta S term. I mean, when the laser hit on the surface of the target, the temperature at the surface of the target is higher than the evaporation temperature of the target materials. So the T delta S term is pretty high than the bulk annealing. That means it's easy to to make the HCO phase stable in using the PLD. So next, what about growing the porous films? I want to introduce these concepts, the ES barrier. That means the atom, there is an additional energy barrier to the atom diffusion at the descending steps of edges. That means the atoms that prefer to be deposited on the top part of the grains instead of the edges of the grains. So this because they have the ES barrier here to impede atom diffusion. So using this principle, we can make the porous films by controlling the energy barrier as well as the kinetic energy of the atoms. So in this work, we want to control the parameters of PLD to control the kinetic energy of atoms to achieve fabricating HCO porous films. Our hypothesis is regulating energy fluence can tune kinetic energy of atoms to fabricate films with tuning nanoporous structure. We use the energy fluence as the parameters to control kinetic energy of atoms. Energy fluence is defined as laser energy on the target surface per unit area, as you can see this image. When the laser hit on the target surface, it will produce the plasma plume. So different energy fluence will produce the different kind of plume. So the low energy fluence will produce the energy, the plasma plume with small volume. However, a very larger energy fluence can produce very the plasma plume with very high and brighter volume. So it's because the energy fluence will influence or change the kinetic energy of atoms. So they will they also will let more materials left from the surface of the target to the surface of the substrate. They also increase the deposition rate. So in our PLD machine, we use the voltage to control the laser energy pulse and the laser fluence. They have almost a linear relation. It's very convenient for us to control the voltage, to control the laser fluence. In this work, the energy fluence increased from 1.1 joule per centimeter squared to 8.1 joule per centimeter squared. Then I will analyze the defects of energy fluence on the field morphology and structure. Result and discussion. First, the X-ray diffraction. Let's see, the figure A shows the crystal structure of the HCO target. You can see the 111 and 002 peaks. And the figure B shows the XRD peaks of the HCO films deposited under the different energy fluence. You can see the peak positions of the films matches well with the target. That means the fabricated HCO films have the same rock salt structure with the target, and there is no secondary phase. Next, we can see 111 and 002 peaks at the same time in the theta to theta XRD peak spectrum of the HCO films. That means the films are polycrystalline films. Next, there is a preferred 111 orientation in our fabricated HCO films. You can see the target part, the ratio of intensity 111 to the intensity of 002 is much lower than that in the thin films. In the thin films, the intensity of 111 is much higher than the intensity of 002. So the fabricated films has the preferred 111 orientation. And the energy influence will change the crystallinity of the fabricated films. At the low energy fluence, you can see there is no diffraction peaks. It's just some amorphous, like the amorphous area. You can see, but with the increasing of energy fluence, the diffraction peaks occur gradually, and the intensity goes higher with the increase of energy fluence. So that means at higher energy fluence, the crystallinity of the HCO films is higher than that fabricated at the low energy fluence. The SEM images can show the morphology of the thin films on the surface. You can see from a low energy fluence to higher energy fluence. They have you can see more obvious gaps or the nanopores on the films. So the fraction and also the element size are also increased with the energy fluence. From these two statistics, we can see the average size of the columnar grains and islands gradually increase. Also, the nanopore size also increase with increase of energy fluence. there are two principles or mechanism can explain this phenomenon. One is stabilization-driven impingement. The other is surface diffusion-driven coalescence. During increasing the energy fluence, that means the deposition rate of the films also increase. So the columnar grain will grow faster than that in the low energy fluence. So the size of the grain grew faster, that they are easier to deposit, they're easier to make impingement or collide with each other to make larger atoms. Also, you can see the small pores between the columnar grains or atoms. There is capillary effect. This capillary effect will drive these columnar grains to collide with each other to make a larger random island. As you can see the schematic, at the low energy fluence, they just very small and thin columnar grains. With the increasing of energy fluence, they're easy to, they tend to grow and cluster. Finally, at very high energy fluence, there are a lot of islands in the films. Also leave a very large nanopores inside. But this nanopores islands, it seems, are not very uniform in size. And arrangement. Next, cross-section view. With the increasing of the energy fluence, you can see the thickness of the films changes a lot. This figure shows how the thickness changes with the voltage and the energy fluence. From 1.1 to 5.8 joule per centimeter squared. The thickness increases with the energy fluence. When we just talked about the deposition rate increases. After the 5.8 joule per centimeter squared, the thickness of the thin film dropped. It's because the energy, excessive fluence leads to rebounding of the atoms or lead to the scattering of the atoms. Very high energy, kinetic energy of the 80 atoms. So these atoms with high kinetic energy will rebound from the surface of the substrate. So the whole thickness of the film drops. Also in the cross-section SEM image, you can see very clear 3D island structure of the columnar grains and islands. Also, you can tell some nanopores vividly. The STEM images shows the structure between the nanocolumnar grains. As you can see, the high-resolution images, high-resolution TM images, the columnar grains, they just around 10 to 20 nanometer in size. Also, the pores are very clear in the from the different contrast in the TM images. Also, you can see the figure D. The fabricated films showed pyramidal shape that matches what we talked in the introduction. There is an ES barrier at the edges of the columnar grains, so which will impede the diffusion of 80 atoms to the edge set, which will lead to this nanopores. also this adatoms, they tend to grow on the top part of the columnar grains. That's why this is very sharp tip at the middle part, but there is kind of low at the edge part because of the energy barrier at the edge is different than that at the top, at the center part of the columnar grains. In the figure F, you also can see some droplet patterns that was introduced by the melting particles in the plasma with the plasma during the deposition or the laser hit the surface of the target. Besides the plasma, some material they just get melt so they produce the small liquid, and the liquid will also jump to the substrate surface to they will come also deposit on the surface. It's a part of the films, which is also which is a disadvantage for the film application using the PLD, since this droplet patterns destroy the local patterns, local structures of the films. Conclusions. In this work, we produced rock salt HCOs, thin films, using the pulse laser deposition. And these films deposited at low temperature, 300 degrees, but still with the single phase structure and well crystallinity. Also, the film structure showed the 3D island structures with connected random shaped nanopores. So we also analyzed the energy influence effect on the morphology and structure of the thin film. With the increasing energy fluence, the columnar grains, they tend to grow and cluster by the force of deposition driven impingement and the capillary driven surface impingement, and these columnar grains or islands will cloud and groove, make the larger islands leave the larger nanopores. So the size of the columnar grains, islands, and the pores, nanopore size can be regulated using the energy flux.